So welcome to part 2 of the mole concept calculation topic, mole concept and stoichiometry topic. So earlier we did some of the introduction to mole concept. We now move on to the actual calculations part where we involve the equations and this concept which we call limiting reagents. Alright, so let's take a look at this part here first. So we are now going to calculate from equations, but first of all we must learn how to read the chemical equation. So this is an example of a chemical equation here. So we have here an acid-base reaction to give us salt and water. So this is a balanced equation. So how do we read this? We read this as 2 moles of NaOH reacts with 1 mole of sulfuric acid to give us 1 mole of sodium sulfate and 2 moles of water. So we read this in terms of moles. Okay, take note, we read this in terms of moles. We can also read this in terms of molecules. Why? Because number of moles equals to number of particles divided by the Avogadro's constant. So this number is a constant throughout all these different reactants and products. So we can also read in terms of molecules. What we cannot do is to read in terms of mass. We cannot say that 2 grams of NaOH reacts with 1 gram of H2SO4 and so on and so forth. Why? Because 2 grams of NaOH is only 0.05 moles of NaOH, and 1 gram of H2SO4 is only 0.01 mole of H2SO4. 1 gram of Na2SO4 is 0.007 moles, and 2 grams of water is 0.111 moles. So this is not 2 moles. This is not 1 mole. This is not 1 mole, and this is not 2 moles. So this is not equivalent. You cannot read the equation in terms of mass. You can only read this in terms of moles, which means that for mole concept calculation, we must always convert all the mass reading into moles first before we begin with the calculation. So let's take a look at example number 1 here. We must calculate the mass of water produced during the complete combustion of 100 grams of hydrogen gas. So what is the balance equation for the reaction? We need to know the balance equation first in order for us to calculate what is the mass of water produced. So let's write out the balance equation first. H2 plus O2 gives us H2O. Balance. Now, the next step is to determine the molar equivalence. So what is the molar equivalent? It is exactly as how you read the question above. Okay, it is how you read the question above. So we know that we have 100 grams of hydrogen gas. Okay, so this equation here shows the molar equivalent. We know that 2 moles of hydrogen gas will react with 1 mole of oxygen gas to give us 2 moles of H2O. So step 1 we must do is to determine what is the number of moles of hydrogen gas used. So number of moles of hydrogen gas used is simply mass divided by molar mass, and we get the value of 50.0 moles of H2 gas. So now we must calculate the mass of water produced. So based on the molar equivalent, we know that 2 molar equivalents of H2 will react and give me 2 molar equivalents of H2O. So from the earlier question, from the earlier part, we know that number of moles of H2 is 50 moles. So if I have 2 moles of this reacting to give me 2 moles of this, it means that if I have 50 moles of H2 reacting, the number of moles of water which will be formed would also be 50 moles. So number of moles of water formed is also equals to 50 moles. So with this, the mass is easily calculated. The mass is simply number of moles multiplied by the molar mass, and we will have 900 grams. Okay, let's try example number 2. I have the equation where hydrogen peroxide decomposes to water and oxygen gas. So I need to calculate the volume of O2 gas evolved when I have so much hydrogen peroxide decomposing. So step 1, we write the chemical equation which is already given to you already. So step 2, we cannot calculate in terms of volume, we must convert everything to mole. So how do we calculate this? How do we convert this to mole? We have the volume and we have the concentration. So this is simply the concentration equals to number of moles divided by volume equation. Number of moles of hydrogen peroxide is simply the concentration times the volume. 1 times 50. Convert this into cm cube. Convert this into dm cube. And what we get is 0.0500 moles of hydrogen peroxide. So based on the mole ratio from the equation here, 2 molar equivalents of hydrogen peroxide will actually react and break down to give me 1 molar equivalent of oxygen. So with this, I can calculate the number of moles of oxygen gas, and this gives me 0.0500 divided by 2 times 1. Okay, 2 times 1, which is 0.0250 moles of oxygen gas. And with this, the volume is easily calculated. It's simply number of moles multiplied by 24, and I get 0.600 dm cube of oxygen gas evolved. Okay, so try checkpoint 13. Pause the video now. Once you have attempted, play the video to check your answers. For checkpoint 13, calculate the volume of hydrogen gas produced at room temperature and pressure when 1.3 grams of zinc reacts with excess dilute sulfuric acid. So first of all, step 1, write the chemical equation. I get the acid metal reaction giving me salt and hydrogen gas. Step 2, convert everything into moles. So 1.3 divided by 65. I have 0.0200 moles of zinc. And based on the molar equivalence, 1 mole of zinc will give me 1 mole of hydrogen gas. So number of moles of H2 is also 0.0200 moles, and the volume is simply number of moles multiplied by 24, and I have 0.480 dm cube of hydrogen gas. For question 2, this is a step question, so it's quite simple. I have 4 grams of CuO, and it reacts completely with all the ammonia. Question part A, what is the amount of CuO reacted? It's simply mass divided by molar mass, 64 plus 16, and I have 0.0500 mole. Part B, what is the amount of ammonia that reacted? From here, I know that 3 moles of CuO will react with 2 moles of NH3. So based on proportion, number of moles of NH3 that will react would be 0.0500 divided by 3 times 2, giving me 0.0333 moles of ammonia. And with this, part C is easy. The volume is simply number of moles times 24, giving me 0.800 dm cube. And part D, it's the same as part B. What is the mass of water produced in the reaction? From the above equation, it is 3:3. So 3 moles of CO gives me 3 moles of water. So number of moles of water is equals to 0.0500 moles, and the mass would simply be 0.0500 multiplied by 1 times 2 plus 16, giving me 0.900 grams of water. Question number 3. I have 67 grams of heated lead 2 oxide here. What is the mass of lead produced? So same, right equation is already given. So part 1, we calculate the number of moles of lead. Number of moles of lead oxide would be the mass divided by the molar mass, and I will have 0.300 moles. So from the equation, I know that 1 mole of PbO will give me 1 mole of Pb. So number of moles of Pb will be 0.300 moles, which means that my mass will be 0.300 multiplied by 207, giving me 62.1 grams. Part B is the same as part A. PbO reacts with 1 mole of H2, 1:1. So the number of moles of H2 is also 0.300 moles, which means that my volume will be 0.300 multiplied by 24. Number of moles times 24, 7.20 dm cube of hydrogen gas is required for the reaction. So do likewise for the rest of the questions. For question number 4, you should have 86.4 grams of silver. For question number 5, you should have 63.1 grams here and 14.3 dm cube here. Question number 6, you should get 0.277 grams and 0.179 dm cube here. And question number 7, you should get 4.32 grams. If you can't get any of these values, relook through the examples I've gone through earlier. They all use the same steps to get the answer. So earlier we covered the calculations of equations using the mass and converting them into number of moles. But what if we have volumes of gases involved? This one will be a bit easier. So let's take a look. So I have this equation here as well. N2 plus 3H2 giving me 2NH3. How do we read this equation? There's 1 mole of N2 reacting with 3 moles of H2 to give us 2 moles of NH3. I can also read it in this way. 1 molecule reacting with 3 molecules to give us 2 molecules. And the volume one is a bit more unique. So if you realize the number of moles is actually equals to volume over 24. If I take 1 mole and divide by 24, I take 3 moles divided by 24, I take 2 moles divided by 24. All these 3 have been divided by the same constant denominator of 24, which means that there is actually no need for me to divide by 24 throughout, since it's all the same. So if I have 100 cm cube of N2, I can say that it reacts with 300 cm cube of H2 to give me 200 cm cube of NH3. So for gases, I can do a direct comparison between the volumes. There's no need for me to convert to number of moles for gases. So let's take a look at the example below. So remember what I said earlier, you cannot do the volume equivalence if it is not a gas, because 200 cm cube of H2 can react with 100 cm cube of O2, but it will not give me 200 cm cube of liquid water. It will give me 200 cm cube of gaseous water or steam or water vapor, but it does not give me 200 cm cube of liquid water. So let's take a look at the example here. The Haber process involving the synthesis of ammonia from N2 and H2. So step 1, as usual, equation N2 plus H2 gives NH3. Balance the equation. So now, let me determine the mole ratio. I know that there is 500 cm cube of hydrogen gas. Of hydrogen gas. And what is the volume of N2 required to completely react with this volume of hydrogen gas? So from the equation above, I know that N2 is equivalent to 3H2. Okay, so with this, I can calculate straight away the volume of N2 required. Simply 500 divided by 3 times 1. And this gives me a value of 167 cm cube. How much ammonia is formed? Same thing, this is equivalent to 2 ammonia. So the volume of ammonia formed is simply 500 divided by 3 times 2, which is 333 cm cube of ammonia formed. Alright, try checkpoint 14 out below. This is actually a pretty easy checkpoint. Pause the video here. Okay, for checkpoint 14, same thing. We do the molar equivalent. 2H2S is equivalent to SO2. I know that this is 80 cm cube of H2S. So what is the volume of SO2 that reacted? It is simply 80 divided by 2, which is 40.0 cm cube. Question 2. Methane burns in oxygen to give carbon dioxide and steam. So let's write the equation out first. Methane burns in oxygen to give me carbon dioxide and steam. So they are all in gaseous state. Make sure the equation is balanced as well. 2 here and 2 here. So what is the volume of oxygen required? I have 10 dm cube of methane. So it's 1 molar equivalent of methane is equivalent to 2O2. So volume of oxygen required is simply 10 times 2, 20 dm cube. And what is the volume of the products form? I have CO2, I have H2O. So volume of CO2 is simply the same as that of methane, because it's 1:1, 10 dm cube. And the volume of H2O is 2 times that of methane. It's 2 times that of methane. 2 times that of methane, so it is 10 times 2, which is 20.0 dm cube. Easy. The next part of mole concept deals with limiting reagents. This part is the stumbling block of most students, but it is actually very simple. So let's think about this in a very easy way. So let's say I have let's say I have 3 cups here. Each one is 100 cm cube. And I have a glass of water here which contains 250 cm cube of water. So how many full cups can I get? How many full cups can I get? I have 3 100 cm cube, but I only have 250 cm cube of water. So at the end of the day, I only get 2 full cups of water. So which one limits me from pouring all the cups fully? It is the volume of water. So in a chemical reaction, there may sometimes be a reactant which will limit the other reactant from reacting completely. So the reactant which limits the other reactant from reacting completely is called the limiting reagent. So let's take a look at the example below. I have 150 gram of magnesium and it is burned in 50,000 cm cube of oxygen and it forms magnesium oxide. So what is the mass of magnesium oxide form? So part 1 of this thinking process is, does all my magnesium react? Is it possible for all of it to react? How would I know? So let's solve the question. Step 1, write the equation which is balanced. Mg plus O2 gives me MgO. Now you notice that there's enough values here, enough data here for me to calculate the number of moles of both magnesium and oxygen. So with this, you should deduce that there's very likely a limiting reagent in the question. So to calculate number of moles of magnesium is simply mass over molar mass. Mass over molar mass. And what do we have for this? We have 6.25 moles. Number of moles of oxygen is volume, convert to dm cube, divide by 24, and I have 2.08 moles of oxygen gas. So if you think about this, two moles of magnesium will react with 1 mole of oxygen. So if I have 2.08 moles of oxygen, it should react with 4.16 mole of magnesium, correct? But in reality, I have 6.25 mole of magnesium, which means that my magnesium is a lot more than what is required. So my magnesium is in excess. It is extra. It is in excess. So what prevents my magnesium from completely reacting away? It is the oxygen. So my oxygen limits the reaction, and I say that oxygen is the limiting reactant. Okay, So based on this, because only 2.08 grams of oxygen is present, it will only react with 4.16 gram of magnesium, which means that the product which is formed, MgO, needs to be calculated with the number of moles of oxygen, which in this case is 2.08. So this is 1:2. So my number of moles of magnesium oxide formed will be 4.16 moles. Okay, so we always calculate the products formed with the number of moles of the limiting reagent. So now let's calculate the answer. Determine the mole ratio. We know that this is O2 is equivalent to 2 MgO. So my number of moles of my MgO is 2.08 times 2. This is 4.16 moles. And to calculate the product form here, it would simply be 4.16 times the molar mass, 24.3 plus 16, giving me 168 grams. Okay, this step should actually be down here. Okay, so this is quite simple. Follow through the 4 steps and you will get the answer relatively easily. So try checkpoint 15 to see whether you have understood the concept of limiting reagent. Pause the video here now. Alright, so for checkpoint 15, what is the maximum mass of calcium carbide that can be formed from 160 gram of CaO and 180 gram of coke? So again, you see that there's enough data here to calculate the number of moles of both the reactants here. So you must straightaway deduce that there is a limiting reagent. So we calculate number of moles of CaO. You will have 2.86 moles. Number of moles of carbon is 15 moles. So based on the molar equivalent, CaO is equivalent to 3 carbon. So if I have 15 moles of carbon, it means that I will react with only 5 moles of CaO. But I only have 2.86 moles, which means that there is not enough CaO to react with all my carbon. So my limiting reagent is, that's right, is CaO. So we do the subsequent calculation with the number of moles of CaO. So based on this, what is the maximum mass of calcium carbide that can be formed? Equation tells me that CaO is equivalent to 1 CaC2. So my number of moles of CaC2 is also equals to 2.86 moles, which is the number of moles of my calcium oxide, the limiting reagent. So the mass is simply 2.86 multiplied by 40 plus 12 times 2, the molar mass of calcium carbide, giving me 183 grams. Now let's try checkpoint number 2. Checkpoint question number 2. So in this question, we have a mixture of 125 cm3 of oxygen and 50 cm3 of hydrogen at room temperature. It is exploded, means it burns. This basically means it burns. And then it is cooled to room temperature. So let's write the equation out first. O2 plus H2 gives H2O. Balance the equation. 2 and 2. So this is gas, and this is allowed to cool, which means this is a liquid water. Okay, so I have enough data to calculate the number of moles, and in this case it is gases, so I can directly compare the volume of gases. So I know that O2 is equivalent to 2H2. I have 50 cm3 of H2, so it should react with 25 cm3 of O2. But I have 125 of O2, which means my O2 is in excess. There's 100 cm3 extra, so which is the limiting reagent. That's right, the limiting reagent is hydrogen. Okay, so what are the gases remaining? I have my O2 that remains. O2 remains, so it's 125 minus 25 equals to 100 cm cube. So this is the O2 which remains. How do we get this 25? It's because we know that H2 is 50 cm cube. So the volume of O2 which reacted is equals to 50 divided by 2 times 1, which is 25 cm cube. So I have 100 cm cube O2 which remains. Is there any water or is there any H2O remaining? No, because this is a liquid and they only want the gases. So answer is simply O2 and 100 cm cube. Question number 3. 24 cm cube of methane is burned completely in 106 cm cube of oxygen. At the end, the products were cooled to the original temperature, which is probably room temperature. So step A, equation for the reaction, CH4 plus O2 gives me CO2 plus H2O. And I balance the equation, 2 here and 2 here. This is a gas, this is a gas, this is a gas, and this is liquid state because it was cooled to the original temperature. Part B, what is the volume of oxygen used up? I know that 24 cm cube of methane was burned completely. So based on the mole ratio of 1:2, my volume of O2 used will be 24 times 2 equals to 48.0 dm cube. Okay, so part C, what is the volume of carbon dioxide produced? From the equation, 1 mole of methane will produce 1 mole of carbon dioxide. So the volume of carbon dioxide produced is equals to 24 dm cube. Part D, what is the total volume of gas that remains? So the gas that remains is essentially the unreacted oxygen plus the CO2 formed. So what is the unreacted oxygen volume? I know 48 was used up. I started off with 106. So unreacted O2 is 106 minus 48, and my O2 and my CO2 form is on top from here 24. So this will give me the total volume of gases left. There's no water. Why? Because water is in the liquid state. So this is not a gas. Adding this up together, I will have 82.0 cm cube. Okay, this is cm. This should be in cm as well. Alright, so now let's move on to the next part of this area of this mole concept topic, which includes calculating of percentage purity and percentage yield. These are actually quite simple concepts. Again, this is a proportion calculation. So let's start off with a very simple example here. If I have Mg plus O2 giving me MgO, if I have 1 mole of Mg, technically I will assume that I will have 1 mole of MgO formed, correct? 1 mole should give me 1 mole. But in reality, I will actually get less than 1 mole. Why? Because of possibly incomplete reaction, impure reactants, I lose some product during the process, and so on and so forth. So I may not get the full 1 mole of MgO. So how much do I get? So let's say I should get 1 mole. I only have 0.9. What's my yield? My yield is 90%. Okay. Sometimes we may also need to calculate the percentage purity of a substance. So let's say we have gold, and in the gold block, this gold is 100 grams, of which only 90 grams is real gold. So what is the percentage purity? It is 90%. Okay, take note, if I have an impure substance, I cannot calculate the molar mass I cannot calculate the number of moles by dividing my molar mass. So if let's say my gold is 100 grams, and this is impure gold, I cannot take 100 divided by the molar mass of gold. Okay, why is that so? It's because this 100 grams doesn't solely belong to gold itself. It belongs to gold and some impurities. So the molar mass is not accurate. The molar mass is not the mass of the gold and the impurity. Okay, the molar mass in this case, if we put the gold in, is wrong because 100 grams doesn't all belong to gold. Okay, yield we covered earlier. So this is actually how much is formed in the reaction versus how much you should get based on calculation. So we can count based on mass, or we can count based on number of moles. In both cases, they will give us the same answer because this is a proportion calculation. So let's try a question to explain this concept. I have 100 grams of calcium carbonate here, and this was reacted with excess dilute sulfuric acid, and it gives me 20 grams of carbon dioxide. What is the percentage purity of the calcium carbonate used? So based on the question, it already tells you that the calcium carbonate is not pure. So you cannot take this mass and divide this by molar mass. Okay, so step 1, we write the balanced chemical equation. CaCO3 plus H2SO4 gives me calcium sulfate, salt plus water plus carbon dioxide. Okay, so this is the balanced equation for the first step. Right, so now the next step. The next step for this question is determining which part of the data we can use to calculate. So we know that 20 grams of carbon dioxide was formed, and this carbon dioxide must have come from the pure calcium carbonate. It must have come from the pure calcium carbonate. So we can calculate based on the number of moles of carbon dioxide, because 1 mole of this will give 1 mole of this. So what is number of moles of carbon dioxide? Number of moles of carbon dioxide is simply mass over molar mass, and we have 0.455 moles of carbon dioxide. So as mentioned earlier, this carbon dioxide must have all come from pure calcium carbonate. Okay, which means that my number of moles of pure calcium carbonate is 0.455 moles. So once we know this, the mass is easily calculated. It's 0.455 times the molar mass, 40 plus 12 plus 16 times 3. I will have 45.5 grams. So this is the pure calcium carbonate. The impure one is 100 grams. So the percentage purity would simply be the pure over impure times 100%, giving me 45.5% purity. Okay. We now move on to percentage yield calculation. So this one is similar to percentage purity, but it is in the opposite way. There's a little bit of twist here. So in this case, we have 100 grams of calcium carbonate reacting with excess dilute sulfuric acid to give me 30 grams of carbon dioxide. What is the yield of carbon dioxide? So when it asks about yield, it means how much of it actually has formed. So by right, I should get how many grams? Maybe by right I should have 40 grams, but I only received 30 grams of carbon dioxide here. So what is the yield of this reaction? So let's do a quick calculation. Step 1, write the balance equation as usual. CaCO3 plus H2SO4 gives calcium sulfate, salt plus water plus carbon dioxide. Now, step 2, we know that this is the yield calculation, so this is a pure substance. We need to calculate by right how much CO2 should be formed. So first of all, we calculate the number of moles of calcium carbonate. This is mass divided by molar mass, CaCO3. I will have 0.999 moles of calcium carbonate. Okay, so based on the equation above, CaCO3 should give me CO2. 1 mole of CaCO3 should give me 1 mole of CO2, which means that my number of moles of CO2 formed should be 0.999 moles. Okay, it should be 0.999 moles. So based on this, it means that my mass of CO2 should be 0.999 moles times molar mass, 12 plus 16 times 2. It should be 43.956 or about 43.96 grams. So this is what I should get. 43.96 grams. But I only received 30 grams of carbon dioxide. So the yield would be what I actually received divided by what it should happen times 100%, which will give me 68.2%. So the yield is 68.2%. Okay. So attempt checkpoint 16 on your own. Alright, checkpoint 16. Question number 1. 4.3 grams of copper was heated in oxygen, and I have 3.2 grams of copper oxide obtained. What is the percentage purity of copper? So based on this, we know that the copper is not pure already. Equation wise, copper plus oxygen gives me copper oxide. Balance the equation, 2 here and 2 here. So I have 3.2 grams of copper 2 oxide obtained, and I must calculate the percentage purity of copper. So copper oxide must have come from pure copper reacting with oxygen. So let's determine the number of moles of copper oxide first. Mass divided by molar mass, and I get 0.0400 moles of copper oxide. So based on the equation, 2 moles of copper should give me 2 moles of copper oxide, which means that my number of moles of copper or pure copper should be 0.0400 moles as well. So the mass of pure copper should be 0.0400 times 64, giving me 2.56 grams. So notice this is 2.56 grams of pure copper. This is 4.3 grams of impure copper. So percentage purity is simply 2.56 divided by 4.3 times 100%, and I have 59.5% purity of copper. Question number 2. Zinc reacts with sulfur. According to the equation, zinc plus S give me zinc sulfide. I have 6.5 grams of zinc here. It reacts with sulfur to give me 9.0 grams of zinc sulfide. What is the yield? So yield means that I should actually receive something more than 9 grams of zinc sulfide. So let's calculate from the front of the equation to the back. So part 1, what is the number of moles of zinc sulfide? What is the number of moles of zinc? It is 6.5 divided by 65, 0.100 moles of zinc. And from the equation, 1 mole of zinc should give me 1 mole of zinc sulfide, which means my number of moles of zinc sulfide should be 0.100 moles as well. And this translates to a mass of 65 plus 32, 9.7 grams. So the yield of this reaction is what I obtain over what I should get times 100%, and I have 92.8% yield. Okay? Alright, the next part of mole concept deals with determining of equations from empirical data. So what is this about? Let's take a look at the example and we find out more about this. It's actually quite simple. It is basically to use the values obtained from an experiment to calculate the equation for the reaction. So in this question, we have 6.2 grams of phosphorus reacting with 4.8 grams of oxygen. It produces an oxide, and we must determine the equation for the reaction. So of course we cannot equate. We cannot say 6.2 grams of P or 6.2 P plus 4.80 gives us something. This is not equivalent because this is in mass. So we must convert all the mass values into moles. So for phosphorus, it is times 4 is P4, 0.0500 moles. For my oxygen, it is 0.150 moles. Okay, so based on this, we can determine the equation already. So I know that 0.0500 moles of phosphorus will react with 0.150 mole of oxygen. And all my oxygen and all my phosphorus here must go into my product because it can't be lost. Everything here must go into my product. So if I do a simplification of the moles here, 0.0500 and 0.150 moles, what is the common ratio? I simply divide by the smallest number throughout, and I will have 1 and I have 3. So this means that I have 1 P4, 1 mole of P4 will react with 3 moles of O2, and it will give me a product which contains all my P and all my O. So this is the final equation. P4 plus 3O2 gives me P4O6. And there you have it. Very simply and very easily done. Try checkpoint 17 by yourself. Pause the video now. Checkpoint 17. Let's take a look. So in this question, you have 11.2 grams of iron. It was found to react with 4.8 grams of oxygen. So we will need to calculate the equation for the reaction as the final step here. So let's take a look. How do we go about doing this? 11.2 grams of iron was found to react with 4.8 grams of oxygen to form an oxide of iron. So all my iron and all my oxygen must go into my oxide of iron. So part A, calculate number of moles of iron atoms that react. So number of moles is simply mass over molar mass, and I have 0.200 moles of iron. Part B, number of moles of oxygen which reacted. Number of moles is simply 4.8 divided by 16 times 2. Oxygen molecules, oxygen molecules equals to 0.150 moles. So now let's do a simple comparison. My iron and my oxygen is 0.2 is to 0.150. So if I divide throughout by the smallest number, I will actually get 1.3 and 1. And this is not exactly a whole number, so let's make it a nice integer by multiplying by 3. You realize this is similar to the derivation of empirical formula. I will have 3 here and I have 4 here. Okay, so I have this ratio of 4 iron reacting with 3 oxygen. So with this, if I write part D, the overall equation out, the overall equation for the reaction, I have 4 iron reacting with 3 oxygen, giving me Fe4O6. Okay, Fe4O6. Do not write Fe2032, because in this case, what you can determine from the equation is Fe4O6 only. You cannot conclude that it is actually Fe2O3 and there's 2 units of Fe2O3. So this is not conclusive, but this is conclusive. Question number 2. 6.7 grams of potassium nitrate. When it's heated, it gives me 5.7 grams of potassium nitrite and 0.816 dm cube of oxygen. I must find the equation for the reaction. Okay, you must find the equation for the reaction. So we could actually write this and balance the equation, but this will not give you any mark because you are supposed to determine the equation based on the values that are given here. So as usual, in all mole concept questions, the first step would be to calculate the number of moles of all the reactants. So let's count for KNO3 first. I have 6.7 grams divided by molar mass 99 plus 14 plus 16 times 3. I have 0.0663 moles of KNO3. So number of moles of KNO2 would be 5.7 divided by 39 plus 14 plus 16 times 2, and I have 0.0671 moles. And number of moles of oxygen is 0.816 dm cube divided by 24, 0.0340 moles. So now we put these 3 species side by side and we do a comparison. KNO3, KNO2, and oxygen. 0.0663, 0.0671, and 0.0340. So doing likewise as empirical formula calculation, we divide throughout by the smallest number, and this is 0.0340. This is the smallest number. Dividing throughout, I will get 1.95, 1.97, and 1, which gives me a nice number of 221. So with these values here, I can now write the equation. KNO3 2 will give me KNO2, 2 of it, plus 1O2. So this way, you will get the full marks for the question. You cannot jump shotgun to give the equation in the first step and then say that's it, this is the answer. Okay, you must calculate everything out stepwise and then conclude that this is the overall equation. We now move on to the last part of mole concept, and that is the calculations involving titrations. This is actually a combination of the concentration calculations part and some other parts in front, which involves limiting reagents and interpreting the equations. So let's do an example, as this is more easy, as it is easier to explain with a simple example here. So for this question here, I have 25 cm3 of aqueous NaOH, and this is required to completely react and neutralize 20 cm3 of H2SO4. So what is the con of my NaOH? So what values am I given here? I'm given the volume of NaOH. I must calculate the con. I'm given the volume of H2SO4, and I'm given the con. So based on this example here, I will be able to determine the number of moles of H2SO4, because con is equals to number of moles over volume, and I have this and this. So step 1, we write the equation first as usual. NaOH plus H2SO4 gives me Na2SO4 plus H2O. Make sure it is a balanced equation. Okay, and we calculate whatever we can with the data we have in the question, which is this part. So number of moles of H2SO4 is equals to volume, convert to dm cube times concentration, and I have 0.0100 moles of H2SO4. Okay, now we know that this is 0.0100 moles of sulfuric acid. How many moles of NaOH will react with 0.0100 moles of sulfuric acid? Let's do a mole equivalence. So 2 mole of NaOH is equivalent to 1 mole of H2SO4, which means that my number of moles of NaOH is equals to 0.0100. This is 1, this is 2, so 1 and 2, so 1 to 2, 2 to 4, 4 to 8, I must times 2. I have 0.0200 moles of NaOH, which will react. So now I have the volume, I have the amount or number of moles. Can I determine the concentration? Yes, it's actually very easy. So con of my NaOH is simply the number of moles divided by the volume in dm cube, and I will have the answer 0.800 moles per dm cube of sodium hydroxide. Okay, let's take a look at checkpoint example number 2. In this case, I have HCl being prepared from a stock solution of unknown concentration. So a 250 cm3 solution of dilute HCl was prepared from 10 cm3 of a stock solution of unknown concentration. So this prepared acid completely neutralized sodium hydroxide. So what is the con of the stock solution? So let's draw some diagrams to explain this question, because it is rather complicated. So I have a stock solution. This is my stock solution. Okay, and I remove 10 cm3 out, and I put it into a new container here. Okay, and this container here, I dilute this to 250 cm3, of which 10 cm3 came from the stock solution. Okay, 25 cm3 of the prepared acid. So this is the prepared acid. I take out 25 cm3 and I put it into a new container. This is 25 cm3 of the prepared acid. is neutralized by so much sodium hydroxide. So I add in NaOH and 12.5 cm cube of 0.5 mole per dm cube NaOH can react away all of my 25 cm cube of prepared acid. So what is the con of the stock solution? We work backwards from here. So what can we calculate? We can calculate the number of moles of sodium hydroxide used. So step 1, write the equation. NaOH plus HCl gives me NaCl plus H2O. Okay, we know that the number of moles of NaOH used is equals to the volume multiplied by the concentration. Okay, this gives me 0.00625 moles of sodium hydroxide. Okay, and this sodium hydroxide here, this is 1:1. One NaOH reacts with 1 HCl, so the number of moles of HCl in the 25 cm cube of prepared solution is 1:1, 0.00625 moles as well. Okay, so this is in the 25 cm cube of prepared solution. So how much of it? 25 cm cube was obtained from this 250 cm cube. From this 250 we take out 25 and we do the titration. So what is the amount of acid in this 250 cm cube? It is simply a proportion. So amount of HCl in 250 cm cube is simply 0.00625. This is in 25. So what is in 250? I multiply by 250. I will get 0.0625 moles. So this is the number of moles of HCl in the 250 cm cube of the prepared acid. And where did the acid from here come from? It came from this 10 cm cube of stock solution. So in fact, this number of moles of acid was originally found in 10 cm cube of stock solution. Okay, this was found in the stock solution. So if 10 cm cube of stock solution contains 0.0625 moles of acid, what is the con of the stock solution? Con of HCl stock. This is found in 10 cm cube. So con is simply number of moles over the volume. This is in 10, so it's 10 divided by 1000. I will have 6.25 mole per dm cube. So this is the concentration of the initial stock solution. This is a complicated question, so if you are still not very clear, please rewind the video and take a closer look. If you are fine with this, move on to checkpoint 18. Attempt checkpoint 18 and then check your answers. You can pause the video at this moment. Alright, so for checkpoint 18, question number 1, 32 cm cube or 0.1 mole per dm cube base NaOH reacts with so much HCl in the titration. Calculate the concentration of the acid. As usual, step 1, we write the chemical equation. NaOH plus HCl gives me NaCl plus H2O. Okay, what can we calculate from this question? We can calculate the number of moles of NaOH. So number of moles of NaOH is equals to the volume times the concentration, 0.00320 moles. And from the equation, I know that 1 mole of NaOH will react with 1 mole of HCl. So number of moles of HCl which was reacted is 0.00320 moles. Okay, so this number of moles of HCl was found in 25 cm cube of solution. So which means that my concentration of HCl is simply number of moles divided by the volume of the solution, which is 25, and I will get 0.128 moles per dm cube. I must also convert this to gram per dm cube. So to convert number of moles to gram, Recall number of moles is mass over molar mass. So to convert number of moles to mass, I simply multiply the number of moles with the molar mass. So I multiply by the molar mass of HCl, which is 1 plus 35.5, and I will have 4.67 grams per dm cube. Question number 2. Again, this is an acid-base reaction. So step 1, we have the equation out first. H2SO4 plus KOH gives me K2SO4 plus H2O. Balance the equation. And what can I count? I have the volume and concentration, which means I can calculate the number of moles of H2SO4. This is 18 over 1000 times 0.2, which gives me 0.00360 moles of H2SO4. And based on the equation above, 1 mole of H2SO4 is equivalent to 2 moles of KOH. So my number of moles of KOH is 0.00360 times 2, which is 0.00720 moles of KOH. So this 0.00720 moles came from 24 cm cube, which means that my concentration of KOH is simply number of moles divided by the volume, and I will get 0.300 mole per dm cube. And to convert to gram per dm cube, I multiply by the molar mass of potassium hydroxide, which is 39 plus 16 plus 1, and I will end up with 16.8 grams per dm cube. Easily done. The last question for mole concept titration calculations is again a acid-base titration reaction. Now we have NaOH reacting with HNO3, so likewise, step 1, write the chemical equation out. So it's NaOH plus HNO3, and it gives me NaNO3 plus H2O. So this is the equation for the reaction. So part A, con of NaOH is very simple. I have 6 grams per dm cube. So now I must convert to mole per dm cube. So the con is simply 6 divided by the molar mass of NaOH, and I have 0.150 moles per dm cube. So why do I divide by molar mass? Because number of moles equals to mass over molar mass. So given that I have 1 in mass per dm cube, to count the number of moles, I divide the value by molar mass. So I get 0.150 mole per dm cube. Part B, what is the amount of NaOH used in the reaction? So this is again a simple question. I use 20 cm cube NaOH, and it reacts completely with 40 cm cube of dilute HNO3. So what is the amount of NaOH used in the reaction? The amount is simply volume times concentration, and I get 0.00300 moles of NaOH used. Okay. Part C, what is the amount of HNO3 used in the reaction? So based on the equation above, I know that 1 mole of NaOH will react with 1 mole of HNO3. So number of moles of HNO3 is equivalent to a number of moles of NaOH, and this is 0.00300 moles as well. Part D, what is the con in mole per dm cube? This 0.00300 moles of HNO3 came from 40 cm cube of HNO3. So the con is simply the number of moles divided by the volume converted into dm cube, and I have 0.0750 moles per dm cube. And to convert this into grams per dm cube, it is simply to multiply by the molar mass of HNO3, and I have 4.73 grams per dm cube. Alright, so we have now come to the end of the mole concept series part 2. If you are not clear about any of the concepts, make sure you relook the video, pause them at the appropriate moments, think through the steps, look at what I've done, and attempt the checkpoint questions again. Make sure you know mole concept really well, because it will be integrated into many other topics later on in your secondary 3 and secondary 4 syllabus. So that's all for mole concept part 1 and part 2. I'll see you in the next O-level chemistry lecture series. Thank you and have a nice day.